Good morning. Would you please take your seats, except for the speaker? So good morning. Welcome to Baltimore. My name is Bernd Müller. I'm the program committee chair for this meeting. I'm very happy that we have a set of terrific plenary sessions this morning, Monday the Cavalry session, and Tuesday with fabulous speakers. And I would like to thank all those in the program committee and at the APS who've worked very hard to make that happen and work. So this morning we have a session that may be slightly different from the usual sessions at the APS meeting because it involves both science and science politics or science strategy. And we begin with a science talk by Francis Halzen, who will talk about the IceCube experiment and what it took to make it happen. Francis is one of those people who proved that you can still have an illustrious career both in theoretical and experimental physics. And you may not be surprised to know that he also won an award in the year 2000 for the best science writing of the year. So today we're listening to him tell us about IceCube.
Okay, it's a great pleasure to be here. Thanks for the invitation. I am going to talk about IceCube, then about what we have seen and what we want to do next. But for this audience, I think it's nice to remind you why we actually undertook this project, what the science is, and how we did it. So, this is a picture of the South Pole, by the way, taken a few days ago, not by me. There are two people there babysitting the experiment. And as you can see from this picture, there's a lot happening at the South Pole. It's an interesting place. You see here, that's the South Pole telescope, well known from CMB measurements. That's the BICEP experiment, well known from CMB measurements. And this is the data center of IceCube. Of course, IceCube you cannot see. It's a mile deep in the ice under that building. So I always start talks on IceCube by this picture. This is pretty much the only astronomy I know. It tells you the number of photons in the universe as a function of their energy or as their function of their wavelength. It was made by Turner 25 years ago. And so you see astronomers have been very good at doing astronomy at all wavelengths of light, from radio to gamma rays. And the idea was, of course, nobody has done astronomy above 100 GeV TeV, 10 TeV energy. So the idea was to try to do astronomy with neutrinos at these very high energies or extremely small wavelengths. So that's what this arrow shows. Of course, the sky is not empty at these energies. There's a particle flux. And in fact, the sky at these high energies is dominated by cosmic rays, some of which have 10 million times the energy of the LHC beam, which of course make them very fascinating objects. People have seen TeV gamma rays from nearby sources, as I already pointed out. And people have done astronomy with neutrinos. It's the nuclear physics of the universe. We've seen the sun. We've seen a supernova in 1987. The subject of this talk are neutrinos that have 1 billion times higher energy. I will try to use TeV as my unit in this talk, but sometime if I misspeak and say PeV, it means 1,000 TeV. So, is this interesting? Well, I mean, it's a particle that's electrically neutral. In this talk, it has no mass. The energies are so high that so a neutrino is exactly like a photon. So you have to do astronomy with it. It's essentially unabsorbed, which means that it reaches you from everywhere in the universe, from back the origin of time, and it can look into places where there are black holes and light doesn't escape. It tracks nuclear processes, which makes it interesting to people like us in this hall. The only problem is that it's difficult to detect. And then a crucial question is, how big a detector do you need to do neutrino astronomy? That was answered by Zatsepin and Berezinski in '69. And the calculation they did was the following. If you take the highest energy cosmic rays on here, they have such high energy that they move through our galaxy without being bent by the magnetic fields, essentially without being bent. So they are not contained in our galaxy, so they are an extragalactic population. So they fill the universe, which means that they live in the same place as CMB photons, 410 per cubic centimeter. And then back of the envelope, you know the target, you know the beam, you make them collide, and so these cosmic rays will collide with CMB photons, produce pions. Pions will decay into neutrinos. So the universe has been producing neutrinos forever through this mechanism. And so if you do this calculation on the back of the envelope, or in very sophisticated ways, you always get the same answer. 1 event per cubic kilometer per year. That was the answer that Zatsepin and Berezinski got. The real answer now for IceCube is 1.2 instead of 1. And so, so what you are looking at is the decay of a pion into muon neutrino, and the muon then further decays. So that's your signal. Why would you think this is worth doing? Well, if you see one event and you're naive enough, you know where it points, and you solve the problem of the origin of the cosmic rays, which we have not solved after 102 years. So it's time to solve it. So, of course, it's difficult to sell this to NSF or anyone else for 1 event per year, so you try to find something better. And so this is a cosmic accelerator. This is a solar flare. And you see these filaments here that are charged particles moving very close to the speed of light. So when you have streams of relativistic particles, you have magnetic fields, you accelerate. What energy do you get? You can do dimensional analysis. If particles are accelerated in this flare, their gyro radius has to be contained in the flare. Otherwise, you don't have the opportunity to contain them and to accelerate. And that tells you that E over B, Q equal 1, V is the speed of light. Everything in this talk is the speed of light, sorry. Oops, yeah. So it means that E over B is less than the size of your accelerator, and E is less than B times R. If you work out this formula, you get 10 GeV. And in fact, if you wait for a day after the solar flare, 10 GeV protons arrive. So nature is very good at doing this. Of course, you cannot get to these fantastic energies I was talking about 2 slides ago. So where can you find bigger fields over bigger distances? Well, right here. You see, this is a supernova remnant. The star exploded about 1,000 years ago, and these filaments you see are pretty much the same thing as what you saw on the solar flare. This cannot quite get you to the highest energies, but if this star had collapsed to a black hole, it would have done what you see in the movie, and in fact it would have done the same thing, but it would have done it in seconds instead of thousands of years. And you can actually explain the highest energy cosmic rays. The only problem with this picture is that IceCube has already ruled this out, or basically ruled it out. There's one more idea, that is that supermassive black holes, the inflows or outflows on supermassive black holes in active galaxies accelerate the cosmic rays. So why am I telling you this? Well, what you now do is you go and work this out. You calculate how many neutrinos you see from these objects. And the result of the calculation is shown on this slide. Here is the prediction for supernova remnants. That's the prediction for gamma ray burst. And this here, labeled GZK for Greisen, Zatsepin, Kuzmin, is the 1 event per per year. You see this is a flat line on this plot, and that is because I have multiplied the predicted neutrino flux by the energy square. The prediction for these calculations is that the energy falls as 1 over E square. And you see this is great, except if you look down here on the left-hand side of my plot, you see all these neutrinos. In fact, as I stand here, IceCube detects 6 neutrinos, 1 neutrino every 6 minutes. And it's not the ones we want to see. That's a background which is shown on the left side of this plot. And we have been measuring with Super K, the Amanda experiment, and IceCube for more than 15 years now. So the interesting thing, however, is if you look at my arrow, that arrow is 100 TeV. So at 100 TeV, you run out of atmospheric neutrinos. So if you see neutrinos with an energy higher than that, one event is still a discovery, no matter where it comes from. And so that's one opportunity to look for cosmic neutrinos and do astronomy. For those of you who are not experts on this, atmospheric neutrinos are created by the same cosmic rays that I was talking about before. They hit our atmosphere, and about 15 to 20 kilometers above your head, they interact with nitrogen and oxygen and produce pions, kaons, charm particles that decay into neutrinos. And of course, they also decay into muons that are long-lived and reach your experiment at these energies. So the way these calculations are done, by the way, although they're not difficult, so you can all do them on the back of the envelope. You have a black hole or a collapsed object. It accelerates your particles, but these objects are surrounded by gamma rays, by dust, and by photons and dust. So you just ask the astronomers what the density of the light is or the density of the dust. Then you observe the cosmic ray beam, you collide the beam with your target, and you produce a neutrino beam. And that's what I calculated on the previous slide. It's not rocket science. So we decided to build IceCube based on this good news. By the way, if you ask how many neutrinos do you see in this band, well, it's not one. It's more like 10 to 100. But that's provided these calculations are correct, which are really, I mean, it's not like doing QED. It's a piece of art, these calculations. But this was good enough to be motivated to build this experiment. And how to do this was pointed out by Markov in 1960. And his idea is shown on the next slide. What he proposed was to go several kilometers deep where ocean or lake water is dark. It's very pure. So you use it as a Cherenkov medium to build a Cherenkov detector. And you look for neutrinos, you look for muons, basically, coming through the Earth. As a muon cannot come through the Earth, it has been produced somewhere under your feet by a neutrino. And if it's a muon neutrino, it makes a muon. These muons at these energies travel kilometers to up to 50 kilometers. So you can collect these events far outside your instrumented volume. And so you just instrument this volume with light sensors, good old photomultipliers, which you buy in Japan. And so you get a lot of them and fill your kilometer cube. So we did exactly this, except we did it with a slightly different twist. We decided to put them a mile deep under the South Pole, where fortunately the National Science Foundation has a station, which you see on the left of this picture. The IceCube project you see on the right, and the runway is where the planes land. So this gives you the opportunity to build such an experiment and to use ice. So, and what was built was exactly what you see on the picture. So a kilometer of ice, 1.5 kilometers deep under the surface. And here you see a cosmic ray muon coming through the detector. which is also triggered with an air shower array that's on top of the ice. And so the kilometer cube of ice, literally, is filled with 5,160 optical modules. So each optical module, each dot on this picture, is a 10-inch photomultiplier, about that thick. That's as simple as it gets. So the important thing is that we actually found a way to build these detectors very effectively. So the way you do this is a heating element that melts the snow at the top, which is about 80 meters deep. And then you just have what looks like your garden hose that puts out hot water under pressure. And you don't drill a hole. You melt the ice over 2.5 kilometers and about the size of your photomultiplier. And when this is finished, you pull it out. And so what you need is a 4.8 megawatt heating plant, and it puts out hot water under pressure to melt the ice. And so everything you saw in this picture, this whole circus, is built on sleds. And so you set up this heating, this power plant. This is a hose which is 2.5 kilometers long and which will drill this hole in in about 2 days. And this is the heating plant. As I said, 4.8 megawatt, that's about 40 car wash heaters, which is basically what it is. And they are just powered by generators. It's as simple as that. And so these are the car wash heaters, slightly souped up. And so the drill is coming out, and now you have a 2.5 kilometer, not a hole, but a place where water replaces ice. And as ice is an insulator, you now have plenty of time. It stays liquid for days, sometimes longer. So here it comes out. And then your circus moves to the next place where you want to drill photomultipliers in the ice. So here you see the optical sensors. They are all waiting when the drill comes out. They are lined up, 60 of them. And then they are deployed on a cable. And the cable will bring down the high voltage and will bring up the digital signals. So in situ, the photomultipliers are turned into digital signals, which are then transmitted over the same cable to the surface. And this is, of course, the last time you saw your equipment. There's no way to get it out. So I told you all this. And so you have to imagine a mile deep. If you could go there, you would see a photomultiplier every 17 meters. And if you look away, another string, 86 of them, 125 meters apart. The crew did this 86 times without failing. It was incredible performance. So in case you didn't get it, this is a muon going through the detector. You see the Mitcherenkov light, and the dots that are lit up detect light, and the size of the dot in this talk will be the number of photons. So it goes from 1 photon to hundreds. So what does the detector see? It sees atmospheric muons coming from the back. It sees atmospheric neutrinos over the whole Earth, including through the Earth. And so remember, we are looking for 10 to 100 neutrinos. So this is a movie of the detector taking data. And you see it just receives these signals from the photomultipliers and reconstruct tracks. You saw this muon bundle coming through. So this movie lasts 10 milliseconds. So it means that we detect 100 billion atmospheric muons per year, 100,000 atmospheric neutrinos, so we have collected about 500,000 by now, and so we are looking for these 10 events. So occasionally you find an event like that. This is 189 TeV neutrino. So it's a muon track. The red tells you that it came through the Earth. You follow the rainbow, red to blue, to see the time. And so this reconstructs the amount of light, tells you the energy. This reconstructs to about 89 TeV. And we saw an event like that about every year, which is kind of the edge we thought of the atmospheric neutrino spectrum. We actually think this is a cosmic neutrino now. And so you just take data and pile this up, and you keep measuring the atmospheric neutrino spectrum better and better. And so at some point, you get a picture like this. This is the atmospheric neutrino flux, and so you see this is the threshold. This is about 1 TeV, where most of our events are. And then you see we trace the atmospheric neutrino flux, but the atmospheric neutrino flux goes this way. And you see, at some point, you see this 3.7 sigma after 2 years. It's exactly what we were looking for. So at about 100 TeV, you saw the flux flatten out, which is exactly this picture, of course. So once you reach the edge of the steeply falling atmospheric flux, you see something sticking out. Only 3.7 sigma. I'm violating the logic here. We actually had claimed discovery of cosmic neutrinos before we saw the plot I just showed you, but this is the conventional way of doing it, and it delivered too. So these, in fact, are two of the highest energy muons. They deposit 500 TeV in the detector, so it means that the original neutrino statistically had several thousand TeV energy. As I said, this is not what happened. We discovered it differently. We were looking for these events. And the bad news is it's 1.2 events per year we are looking for. The good news is they have 1 million TeV energy, so they are hard to miss. And so you do an analysis, blind analysis, all this is for show. You just look for some huge event. And we didn't find one, but we found this event. And you see this event, the light starts inside the detector, and you see the light travel up and down a string. Then if you wait for a while, the light reaches strings that are 125 meters away. And then it reaches strings that are even further away. And so this event is beautifully contained in the detector. There's no muon track. Don't look for it. There isn't one. This is an electron neutrino. So what that means, an electron neutrino gives most of its energy, 80%, to an electron that showers in the ice. It makes electromagnetic particles that all start radiating, Cherenkov light. But that shower is about 10 meters long. It's a cigar that's smaller than this room. And that in a kilometer cube detector is like turning on a light bulb, which is exactly what you saw. Fortunately, this is a muon track, by the way, of the same energy. It's also a real event. You have to now remember how big this event is. So this is the event superimposed on the data center in Madison. And you see, if you take 6 city blocks anywhere, that's the size of this event. We timed these events, these photons. There are 100,000 photoelectrons in it, which we timed to nanoseconds. And that means that the timing gives away the direction of the event. We're still working on that, but we can do about 10 degrees now, and we are basically limiting by computer. We'll do this much better later. So we found 2 of these events. Remember, we were expecting 1 event per year at 100. We had 2 events above 1,000 TeV. So we didn't claim anything. Also notice they are isolated neutrinos. At these energies, if they were produced in the atmosphere, there will be muons accompanying them. There's no sign of an air shower. And so we didn't claim anything, but of course you all realize by now you want to find more of these events, because as energy is the key in this analysis, you want to contain them in your detector so that it's a full absorption calorimeter. So you just do what everybody has thought of by now. You just build a veto around your experiment, and you still have a 420 megaton detector. And so you look for events like the one shown on the bottom here that starts, it doesn't matter whether it's, whether it's a muon track or not, but you look for an event, and when you track it back to your Vito region, there's no light. Then, in fact, again, not what we did, but you can just plot the events. These are the events in 1 year. And on the vertical axis of this event, of this plot, you see the number of events. On the x-axis, the number of photoelectrons, so you see from left to right, you see the energy of the events. And on the y-axis, you see the number of photons in the Vito region, which you want to be 0. And so the idea is that the interesting events are here at the bottom and the right. And you see here, I lost my mark there. So you see the events tailing off, and you see here the signal sticking out. No analysis involved. We have 4 years of data. Every year of data looks exactly the same. So if you project this on an axis where you show the number of events versus energy, you see again what you have seen before. You see a flux that follows the atmospheric flux and then tails off and exposes the cosmic signal. We actually found 28 more events, and then we were confident enough to claim discovery. And in fact, in the 3rd year of data, we found an event that has more than 2,000 TeV energy. Oops, I'm going backward, sorry. So of course, here you see another plot. This is 3 years of data, so by now the signal is more than 5 sigma. And so what we saw in the contained event analysis is compatible with the true-going muon analysis, which I showed in the beginning, which you see at the bottom right. So that's the story as it stands now. Now, you may think the interesting question is, where do they come from? Well, yeah, that's an interesting question. So let me answer that first. We don't know. But we know a lot. This is the direction of the neutrinos plotted in a picture of the sky. You know, each event is a pixel in this map. And the horizontal, to show this red line, that's the galactic plane. So if you look back at where the events are, you see many of them are far outside the galactic plane. So this is an extragalactic flux, except maybe with a component of galactic sources in it. We don't know. The evidence is not great. So the evidence for this blob you see near the galactic center at the moment is 7.2%, which is certainly not something to get excited about. If you ask the question, do the events correlate to the galactic plane, that still has only a probability 2.8% of being explained by background. Again, it's a 2 sigma. It's not good enough to claim. So it's a mostly extragalactic flux that produces equal numbers of all flavors and with maybe a galactic component. Now, the real interesting question is the following. I should have told you this at the moment I showed the slide, but remember, your accelerated protons interact with gamma rays in all these models and produce a neutron and a pi plus. Occasionally, of course, each time they do that, they also produce protons and pi zeros. And if you count on your fingers and worry about oscillations, for every PeV neutrino we see, a PeV gamma ray is produced. As I showed you on my first slide, nobody has ever seen a PeV gamma ray. But we know, if we have the physics right, as it shows, for every neutrino, there's a gamma ray of exactly the same energy within a factor of 2. Well, why don't we see these gamma rays? Well, these gamma rays don't make it here. Remember, the universe is filled with all this light, including CMB and infrared photons. And PeV gamma rays won't get here. They won't interact with the background light, produce an electron-positron pair, then produce showers. So, but what I can do is, I mean, we know the the background in you know it well enough to do a simple calculation where I take the gamma ray flux that accompanies the IceCube neutrinos and propagate it and see what arrives at Earth. And it arrives at Earth with energies of typically 100 GeV to several hundred GeV. And this is the result of the calculation. The black line here is a fit. It's not a fit, actually. You just plot something that fits the neutrino data that seems to have the right slope. Then I say there's an equal number of gamma rays. I propagate it, and you see when it arrives at Earth, it exactly fits the extragalactic flux of the Fermi satellite, which is something I or probably nobody else expected. But it's that simple. Sorry. Where am I? Okay. So that's interesting. Can I avoid that conclusion? Well, I did something like some models may predict a flux like this, and you will agree this flux doesn't quite fit the data. But still, if I propagate the gamma rays, I must get more than 10% of the Fermi flux. So my conclusion of this is that at least several tens of percent of the gamma rays seen by high-energy gamma ray astronomy come from the same sources as our neutrinos. So that means in the non-thermal universe, which astrophysicists told us is all electromagnetic, there must be a big role played by a significant and possibly a total role by hadronic accelerators. So what's interesting is not that it's unexpected. What's interesting is that I can now go and take their sources and convert them to neutrinos. This works in both ways. And so you can see on this slide, which I won't explain, what you have to conclude from this slide. If I take interesting sources, we should see about one neutrino from that source, which is right at the edge of our sensitivity right now. So unless there's something wrong with this argument, we are at the threshold of seeing sources and should see them within years. Of course, that's again what we expected. IceCube was built to make a detection of sources in 5 years of data. So we're again right on time. So, of course, this is going on now, and you know, obviously the game now is to take catalogs of gamma ray sources and match them to the neutrinos. The action is actually not in the plots I show you. The action is in the muon neutrinos that I showed you at the very beginning, which we can reconstruct to 0.3 degrees, sometimes better, sometimes worse. And that's where we can have a good chance correlating the sources. So the question is, what do you do next? What you really want is a detector that's 10 times bigger. We have now collected 100, 200 of these events in 4 years between these two analyses. But you want thousands of events to do the type of astronomy that I am anticipating. And so you need a detector that's 10 times bigger. It's exactly what you need. And then you have a telescope. So how difficult is that? What you want, you would conclude from what I told you up to now that this is very difficult. But remember, we have a reliable method to deploy these sensors. And we know how to do this. There is another piece of good news besides discovering a flux from the cosmos. The other good news is that while building and calibrating this experiment, we obtained the results shown on this slide. What you are looking at is the absorption length of light from the top of the detector on the left to the bottom of the detector on the right. Now, we knew this ice was transparent. We suspected it when we built IceCube. We had seen ice over shorter distances with Amanda, but we didn't quite anticipate at the bottom of this detector, the absorption length is on average more than 220 meters. Now you have to calibrate this by knowing that the clearest water in the Super Kamiokande detector has an absorption length of 80 meters. So everywhere in our detector this ice is clearer than the best water you can distill, I mean, which is what Super K actually does. Of course, it means if you collect light from hundreds of meters away, it will scatter on the little bit of dust. And so this is something we have learned how to deal with. So, but the bottom line is that instead of spacing these strings by 125 meters, we can probably space them by 250. And you see how this scales on the slide I passed over. You can detect, if we scale them, for instance, by 250 meters, you can instrument 10 kilometer cube with the same number of photomultipliers for the same price. And that's, of course, too good to pass up. So this is what it looks like. You see in red, you see IceCube, and the blue is the 10 kilometer cube detector. Takes 120 strings. We can make the strings longer. We understand the ice better now. And so we are going to propose to do this. This is propaganda, which I can skip, but I just want to point out that there is a similar effort going on in the Mediterranean. So my important conclusions are exactly what I already showed you. That is that I had to actually, after brainwashing you, how we saw 28 events in 2 years after building a 10-year project, we saw actually a flux that was enormous. Remember, we only see one, even with 100% efficiency, at these energies, we only detect 1 in a million neutrinos. The rest flows through your detector. So on an astronomical scale, this is actually a huge flux we discovered, which is consistent with having the same origin as the high energy flux seen by Fermi and by the highest energy gamma ray experiments. And if this picture, if we are not fooling ourselves, of course there are theorists that think this is dark matter. I'll settle for that, but I wouldn't bet my wallet on it. We are close to identifying point sources. Thank you very much.
Who has not been brainwashed? Please, go to the microphone.
Yeah, okay, it's a rather technical question, so I apologize in advance, but your IGRB, your isotropic gamma ray background, the observed didn't match your predicted curve at a GeV. Do you know why?
No, because I thought that this was something that was easy to calculate. You know, you take the fireball model, and astronomers know how many photons are in the fireball. And if they accelerate the cosmic rays, we know how many protons are in them. And so it's just a simple back of the envelope again, which of course Waxman and Bacall did 15 years ago. And it's an easy experiment because we just look for neutrinos when a gamma ray burst happens, and we point in that direction, and we don't accumulate background because it only lasts 10 or 100 seconds. So it's an easy calculation, an easy experiment, an easy observation, and they don't match. Theorists try to lower the predictions, of course, which you always can, but we were faster than them in improving the limit, so it still looks bad. But on the other hand, astronomers tell me that the fireball model doesn't work anymore. So maybe there's something, or maybe it are gamma ray bursts, but they are not something that an astronomer would classify as a gamma ray burst. So it's still possible. I wouldn't rule it out.
Thank you.
You mentioned the connection to the possible dark matter origin of the high energy gamma rays. And I wondered if there is either a way to exclude or a signature in the neutrino detection that would accompany it?
Well, I'm not going to go back to the slide, but it's very simple. What these papers assume is that, of course, we're living in a halo of dark matter, and that particles have PeV mass, 1,000 TeV mass, 3,000 TeV typically, and they decay into neutrinos. Perfectly reasonable model. If that's true, the positions on the map have to correlate to the halo. And these calculations show it does. It's straightforward, it's consistent. It's of course not overwhelming in evidence. Also, if you looked at the data carefully, there is a hint that there is a dip in the spectrum at a few hundred TeV, which would of course be the decay feature of these 3,000 TeV dark matter particles. I have probably now spent more time on it than it's worth, but as I said, it's an interesting speculation. It shows how you have to be prepared in this business to be surprised.
Well, thank you. That was a good last word. Science is all about surprises, and we're glad there are many that still come forward. So thank you very much,
Thank you.
Francis.
Thank you.